G'day guys, and welcome to the lesson on circular motion, in which we're going to look at how slanted planes, which we've covered in other videos, can be brought into circular motion questions to make it a little more difficult. In the top right, I have our circular or centripetal force formulae, and below it I have a new formula which we'll look at later, and we'll actually look at how that one's derived. Now, the best way of describing how a slanted plane can be brought into circular motion is for me to do a question involving a slanted plane in which an object is moving in a circle. Hopefully everyone knows what a velodrome is. A velodrome is it's not usually circular. We're going to assume it's a circular track which a bike rider rides around at a constant velocity. Constant speed. The velocity is always changing. So if a rider is moving around in a perfect circle at a constant speed, we know he must be obeying these centripetal force formulae. So let's put in a few figures. Say the radius of the circle in which the rider is riding. This is a bird's eye view of the velodrome. The radius is equal to 10 meters. And the mass of the rider is 100 kilograms. And the velocity is, we don't know. If we assume that this rider here is riding on this slanted plane, and it is frictionless, we can use what we know of centripetal acceleration and slanted plane normal force reactions to figure out exactly how fast this rider must be going in order for him to neither slip down the plane here or up the plane. Now use your intuition for a second. If the rider was going way too fast, this is a cross section sort of sliced into the track like this. If the rider was going way too fast, he wouldn't be able to stay on this path. He'd veer off and off the edge like that. And if he was going way too slow, then since there's no frictional force, he'd come down towards the center like that. But if he was going at just the right speed, he'll sit on this green line and keep moving in circles, well, ideally forever. So let's figure out a few things. If he is indeed moving in a circle, the net force must point towards the center of a circle. And think about this cross section. This green line here, imagine this is behind the page. He's going around, and he's coming towards the page, and bam, he punches through the page and keeps going around. He's moving in that big circle. Then the center of the circle, a lot of people make this mistake. They think the center of the circle is down here. It's not. It's up here. So that is the line pointing towards the center of the circle that he's making. The net force must act in that direction to keep him moving in that circle. So that's going to be our first assumption. The net force is in this direction. So let's draw in a few forces on this rider, represented here by a box for simplicity, in order to show what's acting on him. We have the weight force, which is 1,000 newtons, and then the normal force, which acts perpendicular to the plane, and we don't quite know how big that force is. And all we know is that the net force should be a little arrow pointing in that direction. Now, with earlier slanted plane questions, we assumed there was no net force. There may have been some friction, or in the end the net force may have pointed down the plane. In this case, the net force is pointing horizontal. Not parallel to the plane, but horizontal. So with that in mind, let's figure out what needs to happen. First of all, if there were any net force in the vertical direction like this, the rider, I might say the box from time to time, the rider would float off or into the velodrome surface, which we don't want. So if we say the normal force here has both vertical and horizontal components, I'll say vertical in purple, I think that was our color code, vertical in purple, and horizontal in red, then that purple vertical component of the normal force has to absolutely cancel out the weight force here in order for this rider to neither move up nor down, or to have net force 0 up or down. So we need to put in some angles. If this is 30 degrees here, this angle in here is also 30 degrees. So the vertical component of the normal force is equal to cos 30 degrees times the normal. And we said just before that the weight force, 1,000 newtons, has to directly cancel out with the vertical component of the normal force. So 1,000 equals cos 30 degrees normal. Therefore, 1,000 over cos 30 degrees equals normal. And normal around about equals 1,150, whoops, it's getting a bit crazy, 1,155 newtons. So we know what our normal force has to be to make sure there's no net force, to make sure the rider is neither sliding down nor up the plane. It's 1,155 newtons. So now we can figure out what this component of the normal force is, because if you look closely, we said there has to be some kind of centripetal force acting in this direction. That's what we said. It can't be supplied by the gravity, because the gravity force acts perpendicularly to that force we want. So it must be that it's this component of the normal force which provides the net centripetal force. So let's look at what that could be. This force here, we'll call it normal horizontal. The normal horizontal force is equal to normal times sine 30 degrees, since it's opposite this angle and the normal is the hypotenuse. And that equals normal times a half. And we know the normal is 1,155, so it's 1155 over 2, which comes to 578 newtons. And that is the net centripetal force acting on this rider. So now we know, hey, what was the original goal? To find the velocity. We know that Fc must equal mv squared on r. So 578 has to equal 80 times v squared on r we said was 10. Therefore, v squared is equal to, whoops, hang on, why have I said mass is 80 here? That was a mistake, excuse me. Mass is 100, so 100 v squared on 10. These cancel down, 578 equals 10 v squared, 57.8 equals v squared. V equals, on the calculator, 7.6 meters per second. Actually, approximately 7.6. So that's how you figure out what the velocity could be if there really are no frictional forces. So to summarize what we went through there, we assumed that there was zero net force acting in the vertical direction. So the normal force, or at least the vertical component of the normal force, has to exactly cancel out the gravity force. And once we've ascertained that, once we've set a normal force that gives us that balancing out, we can say, hey, that normal force not only balances out the gravity force here, but it also provides just a little bit of centripetal acceleration. And that centripetal acceleration corresponds to a velocity of 7.6 meters per second. Now for the really fun part. We'll show how this formula up here would actually give us that same result. Okay, here we go. So, here's our angle. We'll replace the angle with theta. So we know theta equals 30 degrees here, but we're just going to leave it as theta. First of all, we know that cos theta n has to balance out the gravity force. And we also know that sine theta n supplies the centripetal acceleration, which is mv squared on r. So let's get n by itself. N is equal to mg on cos theta from there. So sine theta multiplied by n, which is mg on cos theta. Mg on cos theta is equal to mv squared on r. Since both sides have the term m, we can divide both sides by m. And sine theta on cos theta is equal to tan theta. So tan theta g is equal to v squared on r. Tan theta is equal to v squared on r g. Looks like I forgot to put that in my formula up there. There we go. So anyone who didn't watch the whole video better not be using that formula. Ugh. So using this formula here, if we want to find out exactly what velocity this guy could be travelling around this velodrome at, we'd say, okay, it was tan 30 degrees was equal to v squared on rg. Therefore, v squared is equal to rg tan 30 degrees, which was equal to 10 times tan 30 is 1 on root 3. So 100 on root 3 is v squared. Therefore, v is the square root of 100 on root 3. Let's run this through the calculator. 100 divided by 3. We get v equals 598 meters per second. And we had before approximately 7.6. So this is a very useful formula. Tan theta equals v squared on rg. Sorry about that. Tan theta equals v squared on rg. To find either, if you know the radius, gravity, and the angle, to find the velocity, or if you knew, say, the radius and the velocity and the gravity constant, to find the angle. Very useful. Now, there's another question here. It can get very, very difficult when you introduce friction. I'm going to try to demonstrate how to solve this problem, but it involves some very big terms, so hopefully this will all work out. G, and I'll just put a little bracket here. This is frictionless. So now let's try to introduce friction. Okay, let's say we knew that the velodrome rider was in fact riding around at 5 meters per second here, with the same radius and the same mass. We said before, if he rode it at approximately 7.6 meters a second, he'd just cruise around this line. But if he rode too fast, he'd do that, and if he rode too slow, he'd do this. In this case, he seems to be riding too slow. But we're assuming here he's riding at 5 meters a second, and he's able to stay on this green track. Now this is more like what would happen in real life. If he is staying on this green track, there must be some frictional force that's stopping him from sliding down into the center. And we're going to look at how that frictional force could come into it. Okay, here we go. We'll draw the slant again. There's the slant. Angle is still 30 degrees. There's the rider. Still 100 kilograms. The weight force still acts here. mg, or 1000. The normal force still acts here. But there's now also a frictional force. I'll give it an R there, which acts up the plane to stop him sliding down the plane. And together, these three forces, this is the key, if he truly is moving in a circle, the net force of all these three forces, summed together, has to point in this direction, and it has to satisfy the circular motion equation. So since in this case we know V equals 5, R equals 10, and M equals 100, we can work out straight off the bat what the centripetal force is. Fc is equal to 100 times 5 squared over 10, which comes to, what is that, 250 newtons. Yeah, 25 times 10. 250 newtons. So the net force, or the sum of the three forces acting on him over here, has to equal 250 newtons. Furthermore, we'll start putting in a few extra details. This normal force has both vertical and horizontal component. So there's the vertical component, and there's the horizontal component. This horizontal component will contribute to these 250 newtons. In the problem without friction, it was the only contributor to that 250 newtons. In this question, both the normal force and the frictional force will contribute to this centripetal force. The normal force will help it, and the frictional force will actually reduce the amount of centripetal acceleration. So the amount of centripetal force, yes, they act in opposite directions. So the normal increases and this reduces. So not only does the normal force have horizontal and vertical components, but the frictional force does too. Here they are. There's the horizontal, and there is the vertical. So this vertical component and this vertical component must completely cancel out the weight force here. That's the first rule we can say. So this angle here is 30 degrees. This angle here is the same as this angle. That's also 30 degrees. So n, remembering this length here is n, and this length here is r. N cos 30 degrees plus r, take away, plus r sine 30 degrees is equal to 1,000. Now if we get, let's leave that for now. Furthermore, the centripetal acceleration, which we've identified straight off the bat, has to be provided by this force here and this force here. So we can say that sine 30 degrees n. Take away, since this is acting the other direction, cos 30 degrees r is equal to 250 newtons. So the net force is there. I've counted this as the positive direction, so this is a positive vector and this is a negative. There's the positive, there's the negative, and there's a positive. Okay, so now we start solving these. What have I got here? I've done it already. Yes, this will be easy. Since we're trying to find the frictional force here, that's the goal of this question. And what's the frictional force? Let's try to get n by itself. So sine 30 degrees n equals 250 plus cos 30 degrees r. Since sine 30 degrees is actually 1/2, we can multiply both sides here by 2 and we get n is equal to 500 plus 2 cos 30 degrees r. Now cos 30 degrees is root 3 on 2, so 2 cos 30 degrees is root 3. So the normal is 500 plus root 3r. Now I'll make it clear up here. We've got one equation there and the second equation there, and we've got two variables in each, so we should be able to solve these. We just used equation number 2 to find this. So now let's sub this information back into equation 1 to eliminate something. Yes, we'll eliminate n. So instead of writing n in here, we'll write 500 plus root 3r. So 500 plus root 3r cos 30 degrees plus r sine 30 degrees equals 1,000. Now we just need to get r by itself. So we've got 500 times cos 30 degrees comes to 433 newtons. So multiplying these together, 433 newtons plus we've got root 3r times cos 30. Cos 3 is root 3 on 2. So that's root 3r times root 3 on 2, 3 on 2r plus r sine 30, that's r times a half, so r on 2 equals 1000. So we've got 3r on 2 plus 1r on 2, that's 4r on 2 plus 433 newtons coming down from over there is equal to 1000 newtons. 2r, simplifying that, is equal to 1000, take 433. Sorry for the slant. So 2r is equal to, what was this? 500, around about. Sorry, this is all approximate. This is approximate here too. 567 newtons. Therefore, r is equal to 284 newtons. And so he doesn't, even though it seems he's going a little bit too slow, and you'd think if there was no friction he would drift towards the center like that. Since there is some frictional force acting in that way, it serves to keep him on the green line. Phew! This is the kind of question that you definitely want to write onto your cheat sheet and bring into the exam, so you have something to compare to.